So you can see here a few of the things I enjoy on the screen. So, you know, Winnie the Pooh, always good, running. I have a couple dogs, and also have a couple kids. They come in my talk later too, okay? So in terms of what I specialize in, so I like to consider myself a human movement researcher with a primarily focus on the lower limb and sports biomechanics. And I mainly research 3 key areas. So the first one is what I'll be talking about today, which is calf muscle function and testing. The second one is injury risk screening to prevent sport injuries, primarily to the ACL. And lastly is running biomechanics and footwear. So if ever you want to come visit me, this is where I live. So my lab is right where that little arrow is. And you can see it's quite different to obviously a hospital setup. So I'm based at in a sports center. It's basically where the rugby 7 athletes train. So it was kind of hard watching the Olympics, you know, the finals between Canadian rugby and the New Zealand rugby, but I kind of had to go to New Zealand because I see those girls train in the gym every day. So quite a different environment, unique experience. You can see here the picture at the bottom there. That's our sports science laboratory. So it's quite small, but it's, you know, what you do with the space that matters. So a beautiful place. So please come and visit me. So I'd like to say I flew all the way from New Zealand just to come give this talk, but that's not quite true. I had the opportunity to watch a chair, a 6 months study leave with Professeure Julie Côté at McGill University. So on the left-hand side, you can see my mountain, which is Mount Maunganui, you know, just basically 2 kilometers from where I work. And now I'm on Mount Royal. So I've gained a whole meter of perspective on life. It's great. So yeah, beautiful kind of environments to be in. So quite fortunate to be able to come back. And also for me, it's kind of coming back to my family a little bit. So I did come with my family. So as I mentioned, I have 2 young kids and a very supportive husband. So Toby, who's 7 years old, and Mika, who's 2.5. And we just went apple picking this weekend, which is what I enjoyed doing as a child. So it was kind of nice to be able to share that with them. So it's been a nice experience. So that's enough about me. It feels now like a long time ago. I did a PhD on the calf muscle. And hopefully not this calf muscle, okay? If you go to your PhD in New Zealand and you type in, you know, you do your systematic literature search and you talk about raising calf, this is what you get, or calf raising. I knew I was in New Zealand. I was like, what is all this? Anyway, so if you want to do a PhD on raising cows in New Zealand, good place to do it. I'm talking about these calf muscles. As you can see, I took a picture of my calves this morning just for the talk. But most of you in the room would probably know where the calf muscles are. You have your medial gastrocnemius muscle, you have your lateral gastrocnemius muscle, you have a deeper soleus muscle, and they all connect down to the calcaneus through the Achilles tendon. They're quite an important muscle group. You know, they help us in this current picture go up concentrically on your toes and then lower back down in an eccentric manner. So it's a cool muscle to kind of study because obviously it's quite important for human function. It's important for developing walking in children. It's also important for physical activities involved in sports, such as jumping and running. And obviously it's important later on in life as well. So we know that calf muscle function is associated, for example, with your 6-minute walk time, as well as your balance abilities, and thereby your risk of falling later on in life. So good muscle to kind of look into. Now, from a clinical perspective, the test that is the most common used to look at the calf muscle function is called the calf raise test, or some people call it the heel rise test. As mentioned, it's the most common clinical test that's used, and it basically involves going up and down on your toes as many times as you can while standing on one leg. So it's more considered to assess the strength and endurance of the triceps surae muscles. And typically, you would prescribe this test being done following the beat of a metronome to pace the exercise at 60 beats per minute, where you go up in 1 beat and down in 1 beat. So it's the equivalent of doing 30 repetitions per minute. So in a clinical setting, most of the time we just count the number of times someone goes up and down on their toes, and we use that as the main clinical outcome. Now, if you go read your Maggie textbooks or your Hislop textbook, where they talk about what is a normal performance, most of the time you'll see that around 25 repetition is considered a normal outcome measure. However, this doesn't account for numerous factors, so things such as age, sex, level of physical activity, body mass index, or SIDE. So during my postdoc, I had the opportunity to get involved in a large study where we assessed basically the performance of healthy males and females performing this task across the adult age spectrum, so ranging from 20 to 80. And basically what we found is that, yeah, okay, doing around 25 is normal if you're in your 50s, regardless of whether you're a male or female. But if you're younger, you'd be expected to perform more repetition. And unfortunately, as we age, we all know that we have some physical function loss and we lose our strength endurance abilities, and this ability declines with age. But actually, if you compare the right or left side or the dominant and the non-dominant side, you actually have a similar outcome measure between side. Now, at first, I thought this was a little bit surprising, but upon reflection, when you think that, most of our walking and, for example, running activities basically use both limbs to a similar extent, then it's probably not surprising that the strength endurance of our plantars flexors are quite similar between sides. Now, recently, it's online first, so it was just accepted about 2 weeks ago. We completed a similar study, but in youth. So we actually assessed the strength endurance in about 200 males and female young youth, basically from 10 to 17. And again, we found in this particular population that 25 actually was pretty normal. So the initial normative values did tend to derive or be applicable to a younger population as well. So this kind of gives us a good target for that age range. So if I talk too fast or you didn't understand, you can just take my take-home message slide. So 25 repetition is normal based on median values, but it depends what population you're talking about. So there's more repetition in younger and more active adults. 25 in children, so between 10 and 17, does apply, but it doesn't apply when you get in adulthood. There's more repetition in adult males up to the age of 60, where we actually then see that females start to outperform males. So there's hope for us yet. And in that sense, using matched norm data is important for interpreting calf raise outcomes. In the absence of these normative values, the contralateral side does seem like an adequate reference if it's a unilateral type of injury. So I've just spent all this time talking to you about the number of repetitions. However, we've long known that just counting how many times someone goes up and down is not necessarily a sensitive outcome of calf muscle deficit. So you can just kind of, expect that someone can lift off the ground to a certain amount, and they might weigh a certain amount, but someone can kind of cheat the test, right? And not quite raise as high. So looking at different outcome measures, so things like the peak height and the total amount of mechanical work that somebody completes during this task is a lot more sensitive to calf muscle function deficit. And this has primarily been shown in, Achilles tendon rupture cases or Achilles tendinopathy. Now, unfortunately, for a lot of clinicians, they don't have access to specialized equipment to be able to quantify peak height or mechanical work. Now, we do know that in recent years, there's been a high increase in the use of mobile applications in health and sports. There was a study done quite a few years ago, and I would expect this number to be higher now, that over 60% of clinicians use apps to collect some form of data to inform their clinical practice. Now, this is great because, apps can be practical, they're more affordable, but only when they've been shown to be valid and reliable. So in certain areas, there's only about 5% of apps available in healthcare that have actually been validated. So it's really important that clinicians take the time to make sure that whatever app they are using is evidence-based. Now, there's this thing that happened a few years ago when we were all kind of constrained in terms of, the research that we could do. And I had a PhD student, and our goal was that by the end of the PhD, we'd have a tool that clinicians could use to be able to quantify these metrics. Now, we couldn't actually collect any data at the time, so we actually flipped the PhD on its head and thought, well, why don't we develop the tool first and then look to validate it and then apply it in some clinical circumstances. Now, in my area, in sports science, there's this guy called Carlos who has a series of apps to help quantify movement in sports. And I had seen this app on Twitter, and I thought, this kind of basically looks at tracking the movement of a barbell. I'm pretty sure we could repurpose the same kind of principle to quantify calf raise performance. Now, fortunately, I emailed him and I asked him if he was open for collaboration, which you need to do when you're in New Zealand because it's far from everybody. So if you want to collaborate, you need to email people. And fortunately, he's like, yeah, sure, I think I can help you. I'm like, awesome. Hence was born the calf raise app. So the calf raise app was developed to facilitate testing in clinics and on the field. It's free, now also available on Android. So you can download it, give it 5 stars, delete it, and we can still be friends. It's all good. But basically, the fundamental principle of how it works is that it uses computer vision to track a circular marker that's placed on the foot so that you can get the vertical displacement of this marker when people go up and down on their toes. Okay, and this is the main outcome that you get. So you get this graphical representation of displacement, vertical displacement over time, right? So you can just imagine here someone going up on their toes and coming back down, going up on their toes and coming back down. And that's the curve that you get here over time. So if you count, in essence, the number of peaks, you get the total number of repetitions that somebody completes. So in this example, 22. You can also then extract the peak height of any one of these repetitions. You can extract a fatigue index. So by comparing the peak height of the first repetition to the peak height of the last repetitions, you can get how much they dropped off during this test. By knowing the height of each repetition, you can get the total positive displacement. And if you know the total positive displacement and you know how much the person what their mass is, then you can calculate the total mechanical work, right? So if someone is heavier and they displace the same amount, well, their calf muscle needs to perform more mechanical work for them to displace that same amount. And finally, for some other reason, not necessarily related to the calf raise test, if you also know how fast they're moving, then you can also take out the peak power during the test. So the first obvious study to do once the app was developed was to validate it against our gold standard laboratory-based equipments, which we did in 2 different cohorts. So we looked at it in healthy adults and we looked at it in athletes, specifically rugby athletes. Wonder why? And I was quite happy to see that, the app versus lab, there was excellent agreement and a relatively low level of errors between the measures we were getting using 3D motion capture and force plates compared to the computer vision metrics. The only exception was the fatigue index, which, the disagreement between the 2 systems was around 15%. So I actually don't necessarily recommend people use this as a metric, but it's still in the app in case somebody wants to look at it. Typically, when you would do the calf raise test in a laboratory setting, the displacement is taken from a marker position on the heel. Now, if we think about good 2D video, recording practices, if you're placing a marker on the heel, what happens to the marker is that it moves up, but then it moves away from the camera, and it increases the perspective error, which is exactly what we saw. So we sought to validate use of the app by putting a marker on the side of the foot, so more in plane of motion, and a marker on the back of the foot. And basically, we found much higher level of agreements when we position a marker on the side of the foot compared to putting a marker on the heel. Hence, the recommendation of the app is to place a marker on the side of the foot to look at these metrics. As mentioned, using good 2D motion capture practices is important. So all the validation of the app was performed with a marker of 2.4 centimeter in size. Now, if you understand 2D motion principles, if you want to calculate a distance from an image, you actually need some sort of calibration. So the way that the app works is that you have to insert the diameter of the circle that you place or the marker that you place on the foot. So mine is at 2.4, but you can use different marker sizes. So in the image here, I have two different markers. You have the black one that's 24 millimeters, and then you have the white one that's 32 millimeters. And you can see here that, if you calibrate the image based on the 24 or the 32 millimeter marker, you get relatively similar outcome measures. But if you don't calibrate, or if you don't calibrate appropriately, so for example, here, if you say the marker is 24 millimeters in size, but you're actually meant to be tracking the 32, you underestimate the displacement. And then you get vice versa. If you apply the 32 centimeter calibration on the 24 millimeter sticker, then you overestimate it by 35%. So it's really important that, if you have a given size, that you use that same size. Once you've changed the calibration in the app, it will always remember that. So it's again, just making sure that there's good 2D video practices that are being applied. Setup is also important. So we need to think about having an appropriate and fixed distance away from the motion. So we want our device to be perpendicular to the foot. We also want to enhance the size of the calibration target, because that gives us bigger or better accuracy in 2D motion capture. And we also want a relatively good representation of the motion. So for the calf raise app, what does that look like? So being closer, so for example, here you can see being 30 centimeter away, the calibration target reflects about 6.3% or 6% of the vertical image. And you can see that the motion of going up and down covers about 1/4 of the vertical image. But I've had users place, the video about 1 meter away from the foot. If you're placing the video 1 meter away of the foot, your calibration target only reflects less than 2% of the image, and your motion only covers about 7%. So your accuracy and your resolution is a lot more decreased if you're too far away. So the recommendation is to actually place the video between 30 to 50 centimeters away from the foot. Okay, so to summarize, the calf raise app can be recommended for use. So we have shown that it's valid and reliable. It provides more outcomes than just the number of repetitions. So you get the key outcomes of peak height and mechanical work. The lateral marker placement is recommended over the posterior marker because we have less errors. The fatigue index shouldn't be used. So I've developed something that I'm happy to say that actually I wouldn't use that metric to inform my clinical practice. And obviously we need to consider setup and appropriate calibration to optimize the quality of the data that's being taken out of the application. Now, because you're probably sick of looking at calf muscles, I figured I'd throw in a video of my girl. So this is Mika. She was a little bit younger, and you can see I was teaching musculoskeletal anatomy, which is a subject that I teach, and she seems to be flirting with the muscle man. And she, how about the skeleton? Good job. All right. So maybe a physiotherapist in the making. I don't know. We'll see. All right. So I'll just like to finish off with a few consideration around testing. So we've talked again about the number of repetitions and how this is used, to guide normal practice. And there's been some research, including from myself, conducted in terms of defining what normal is. Now, a lot of the time, this actually doesn't consider foot position. So if you read the clinical textbooks, you'll see that the test is performed quite often from the floor. If you look in the research, actually the test is often performed on a 10-degree incline because it's deemed to be more functional and you get a greater range of motion. Now in sports, it's quite often performed with the heel on the edge of a step. So Having a mechanical mind here, I'm thinking, well, these things are not quite the same, and they are likely to influence the outcomes and the measures that were extracted. So we actually use the calf raise app to look at how foot position influences the calf raise test outcome. And sure enough, what we found was that when you were doing the test from the floor, people were able to complete a greater number of repetition than from the incline, than from the step. A similar pattern was observed when we looked at the total amount of mechanical work that people could complete. So because they were doing a greater number of repetition, then they had greater mechanical work from the floor, then from the incline, then from the steps. So from a clinical perspective, a lot of the normative values, including from my paper, have actually been done with the foot from the step. So when I said 25 is normal, well, actually it's normal if you're doing it on a 10-degree incline and you're a man and a woman in your 50s. And actually, if you're doing the test from the floor, you need to increase your expectations in terms of the total number of repetitions that individuals are performing. So if you were feeling pretty good about yourself, you need to go back out there and train your calf muscles a little bit more. Yeah, so we tend to underestimate the number of repetitions that people can actually achieve during this test. The other one that we've started to look into is how cadence influences calf raise test outcomes. So I told you at the very start that most of the time people perform this test following the beat of 60 beats per minute, where they go up in one beat and come down in one beat. Now, this kind of comes out of a little bit of nowhere. When the test was first being used, researchers said, oh, well, it approximates a little bit the speed of walking. Now, I'm not actually sure anybody has actually looked at that. So here's another potential master's project to look into. But anyway, so 60 beats per minute tends to be the most common. But in the dance literature, for example, they use a much slower pace. So they use 30 beats per minute. So about 15 repetitions per minute during the calf raise test. And in certain sports, they're actually interested in completing the test at a higher cadence, so up to 120 beats per minute. So again, we use the calf raise app to be able to start to look at how varying cadence influences calf raise test outcomes. And here, actually, what we found is that cadence didn't influence the number of repetitions, which in a way is a good thing, because if people are implementing the test at different cadences and they're relying on the number of repetition, then the normative values out there can be applicable. However, the same wasn't true when we started to look at, the mechanical work, where we actually saw that mechanical work was maximized at that 60 beats per minute cadence. Okay, so what does this actually mean? Well, it means that it kind of appears sensible to keep on recommending that 60 beats per minute for now, because it appears to maximize the mechanical work that the triceps surae muscles can do during this test. There does appear to be the existence of a U-shaped relationship, whereby when we increase the cadence or we slow down the cadence, the mechanical works drop. So it could be that 60 beats per minute is the preferred movement velocity for this task that maximizes the outcome, but that actually has yet to be investigated. So maybe actually 70 would be better, or 45 would be better, but we don't know. At the moment, if you're looking at 30, 60, or 120 for the calf raise test, and you want to look at strength endurance, 60 seems like a good number. So at the moment, during my study leave with Julie, what we're actually trying to tease out is whether or not the muscles work differently at 60 and 120, and if there's potentially a sex difference in how people adapt to differences in cadence during the calf raise test. So more to come in this space. So the key take-home message from these kind of clinical studies is that foot position and cadence does matter when we prescribe the test for most of the outcomes. So outcomes from testing in one condition don't necessarily generalize to another condition if we change the parameters of the test. At the moment, the floor or the incline seem like good options, because when people use the step, they don't have an endpoint. So they don't actually tend to increase their range, they just tend to hover. So they go up and they come back down, and they don't go all the way back down. So when you give them that 10-degree incline, you actually give them an endpoint, for them to get to. So it tends to maximize the displacement more than if you just have the heel going off the steps. And as mentioned, the 60 beats per minute seems like an okay cadence to recommend until Kim does more research in this space. And lastly, I just want to highlight that I've talked about all these parameters in the context of the calf raise test. Now, there's specific situations. So for example, Achilles tendinopathy, that we want to start for a slower cadence, for example, and you want to build up to a higher cadence for rehab or exercise purposes. So selecting parameters from a rehabilitation perspective or a training intervention needs to take into account what the end goals are. So my recommendations here are for the calf raise test and aren't necessarily for a calf raise exercise, which is different. So I just like to finish with something that's from, New Zealand. So in New Zealand, we tend to kind of close meetings or start meetings with a whakatoki, which is a Maori kind of proverb. And in this case, I thought this one was appropriate. So with your food basket and my food basket, the people will thrive. So I'm here to like connect and network with other people. And I'm hoping that, Julie and I can thrive together. And as mentioned, New Zealand is quite isolated. I'm the only biomechanic researcher within my program, so I'm always open for collaborations. I know I'm probably a little bit different to what you guys are doing, but I'm still would like to throw it out there. So yeah, so I hope you enjoyed that talk. And
Can you mute yourself 1 second, Kim?
I can try. Yep. I think I'm muted. Yep.
Well, thank you, Kim, for this amazing presentation. It was really, really nice. Before we start with the questions, I would like to thank Julie Côté, who is here, who introduces to Kim. And we've been sending emails back and forth until we found a date that worked for all of us. And so thank you, Julie. Come more often. And yeah, so if you have questions or comments, Kim is here to answer them. I will mute myself and you mute.
We can't hear the conversation that's going on behind you,
I'll unmute it.
Ray. Maybe you should unmute yourselves. Thank you.
So yeah, maybe come here.
Now we have to. So sorry, mine was still muted.
Should I? You should mute yours. Mute.
Mine?
Yes.
Okay.
Can you go there, Julie?
Sure.
See ya, Eva.
So I was just saying it was very praiseworthy that Kim had taken this relatively simple test, but covering all perspective and even developing an app. So my first question is whether data can be sent to the cloud, and the more people use it, the more the cloud gather the data. I think the more it would be valid for norm development across sex and gender and ages. And, yeah.
I completely agree. But the infrastructure is not set up that way. And with the data privacy laws of different country, I think that would be kind of quite difficult. So at the moment, if you download the app and you're testing your patients, it's stored locally within your system. So I guess a way to be able to do that would be to kind of form a specific research project where then, because you can't export the data,
Right.
and then and then export to a
yeah, we had to deal with that for our I mentioned the Vista, the visual search scanning. It's the same, and the cloud in Europe is different from the cloud in North America. So what the way we overcome it was we have data that can be stored to the environment, the clinical environment, or the laptop, or the whatever local environment, and it also can go to the cloud. But the clouds to talk to each other, it's not trivial.
Yeah,
Yeah.
yeah,
But it's
yeah.
worthwhile to look into it.
Yeah.
The other thing I think is you should throw away the fatigability index or,
Yeah.
like fatigue index. Have you looked at areas under the curve? For example, normalizing to 100% with the peak. And then this is like, time is like in seconds. So you can have an area of percent second, and then the total area that repetition generated.
Yeah, I guess in some ways that would kind of reflect the total mechanical work. But yeah, I mean, I think the fatigue index or the drop off is good because often one of the kind of test cessation is people saying when there's a marked decrease in height, but whatever that marked decrease is, it's quite subjective. So you can kind of use it as a threshold to say, okay, well, if it's actually dropped off by 50%, for example, then, void those repetitions and like not count those data.
But other than that, the loss of coordination, so becomes more irregular, for example.
Okay,
I think,
yeah.
But anyway, I would encourage you to still find like a way to look at the fatigue index, because I think it'll be very useful for in rehabilitation and also in sports.
Yeah.
Yeah, like included. Yeah, it's a good suggestion not to drop.
Yeah.
Yeah, I just had a question.
Come closer.
I just had a question. In terms of, do you find the test is as reliable if you wear shoes?
Yeah.
Yeah.
I get
But-
that question a lot,
Yeah.
and no one has actually looked at it. So yeah, you want to come do a PhD? No, in New Zealand, I got a nice lab.
Just dropped out of her.
Yeah, okay, not the right time, I see. No, but that's a great question. And so I personally prefer to do the test barefoot, because it takes away the effect of footwear. So like I mentioned, one of my areas of research is running footwear, and we know that running footwear influences the way you run and the way you move and things like that. And if you're tracking, for example, a marker on the shoe, you can still have movement of the foot inside the shoe that then isn't represented by the footwear. And the other thing is, some people nowadays have massive heels on their footwear. So all of a sudden, instead of being here on your incline, you're here, so that difference in where you're actually moving has an influence. So I would think that it's less accurate and less representative of calf muscle function if you're doing it in the shoe.
Because it is interesting in the sense that I think it's one thing for elite populations, but when you look at populations that have like a really decreased autonomy, they're going to be encouraged to wear shoes indoors all the time. And so even if those shoes will reduce their peak power, reduce their capability, like that's also going to be the most reflective of kind of the force the work they're going to put in every day.
I would expect them to be highly correlated.
Yeah.
In the sense of, if you had tested someone barefoot and then in shoes, I would expect those two values to be highly correlated, but they wouldn't be the same. And what I, again, would base from a basic standpoint or mechanical standpoint, because you're potentially reducing the height or the displacement that they're doing in the footwear, that they would do more repetitions in the footwear than barefoot, marginally.
Yeah.
So I think it's a good proxy, but I'm not ready to say that it's apples and oranges, or apples and apples,
Sure.
Yeah.
And then my last question is, stay there until that was your question.
My last question is, what's like the main barrier to having like a predictive formula for calf raises? Like as we have for VO2 max or as 6-minute walk test? Like what's the main kind of barrier to that, would you say?
Well, I have a predictive equation in my 2017 paper. You can have a look
have
at
it. Okay.
Yeah. But it's a healthy population.
Okay, that's
So so it's based on sex, age, body mass index, and physical activity level scored as a 1 to 6 scale. And then if you input those values, then it will tell you, it will predict or give you a number of what is considered normal within those parameters. So that is available. And I'm actually collaborating with a group of researchers in the Netherlands and the UK, where using the CAFRAISE app, we've now also quantified mechanical work and peak height. So to come, there's going to be some predictive equations for the mechanical work as well.
Awesome.
Yeah. So I guess the main limitation would be, to Joyce's point, is trying to get a large enough sample that you have, that kind of ability to be able to develop those predictive equations. Yeah.
But it's still good to have like the jumping off number. Okay, thank you.
Yeah.
In my world, they're saying that the 5 times sit to stand is really important as a measure, and it also gets balanced. I was curious if it links to the heel weight.
I've never looked at it.
Okay.
Yeah. But to me, I guess the sit to stand, I guess I'm not familiar with how much the calf muscles would be involved in that task, or if it's more, like kind of quad and glute dominant task.
I would think it's the entire leg because
Yeah.
they're not holding, so they have to get up, balance, and sit down
Yeah.
as quick as they can. So it's
That's
like-
just correlating it to the goal.
Yeah. Yeah, looking at if there's an association. Future things to look into.
More questions?
More
I have
questions?
a question,
Oh,
if possible.
Go ahead.
Wait, can you hear me?
Yeah, we're good.
Okay, well, thank you for the presentation, first of all. So how would you define like the minimum height requirement for a successful repetition in the calf raise test?
Yeah, so again, that comes back to what is normal versus what is, what you would expect as a threshold. So using the CAFRAISE app, what I've seen in terms of like average values is around 8 to 10. So 8 to 10, and that's from like wherever you start to like the top of the raise. So again, it depends if you're starting from the incline or if you're going from the ground. In terms of conducting the test, most of the time you would stop the test if you visually appreciate a drop off of more than 50% of whatever that person's maximum height would be.
Okay.
Yeah.
Also, what do you think about people using hands or fingers on the wall to stay stable?
Yeah, absolutely. So typically you get people to use 2 fingertips, shoulder height at the wall. During my PhD, we actually had a dynamometer where we monitored how much force people were putting. And you'd be surprised how much force people can put through 2 fingers to actually help them push up. So it is really important to kind of try to minimize that and really just use, like at the wall, they're not pushing down quite so much. So it's really more for balance. So for my PhD, we kept it at 2% of their body mass. So they had to kind of self-monitor and not exceed putting 2% of their body mass through their fingers. On this force sensor.
Great, thank you. Yep, great answers. Thank you.
Any more questions?
Okay, well, thanks. Thanks everyone for coming. And there's another Talking Research next week on Thursday. Sarah, who is here, will be presenting her research. So I will see you all next Thursday. Thanks again for coming. Bye.